sampling distributions. And we're going to talk about the normal distribution, the central limit theorem, and the relationship to the t-distribution. So the first part of this should be a little bit of review, talking about the normal distribution. So the normal distribution has this density function, and it's determined by two parameters. What's called the Greek letter mu, which is the mean of the density function, and that controls the center or the peak of the graph that you'll see on the next slide, and sigma, the standard deviation. That represents the spread of the data. Okay. In this instance, the probabilities are given by the area under the curve, and the normal distribution curve looks like this. So you can see that the the blue, the red, and the yellow, they all have a mean of 0, so they all line up right here. The green curve, however, has a mean of -2, so its peak occurs at -2. So the mean controls where the peak is, and the three curves, the blue, the red, and the yellow, they all have different variances. So the variance gets larger as the peak starts to decrease. So that indicates there's more spread to the data. So for example, this yellow or gold colored curve, it has a much higher probability of having an observation between 2 and 3 because its area would be all of this right here between 2 and 3 that's under the yellow curve, whereas the blue curve, it has nearly 0 area between 2 and 3. So much less likely to see an observation between 2 and 3 for the blue curve. Okay. So the normal distribution occurs quite commonly, and such as with body temperature, and it can be an indicator of sickness. So the normal body temperature is believed to be about 98.6 degrees Fahrenheit. So how unusual of a temperature would perhaps 100.4 degrees Fahrenheit or hotter be? What what is considered to be a rare body temperature? Okay. And so here, the normal body temperature is 98.6 degrees Fahrenheit, and we're going to assume population standard deviation of 0.773 degrees Fahrenheit. Our goal is to calculate the probability a randomly chosen individual has a temperature that exceeds 100 degrees Fahrenheit under these conditions. So we're going to assume a normal distribution here, and we want to calculate this probability. In order to calculate that probability, you can use Python, you can use a calculator that's linked here, or you can use a table, and the table is in the back of your book. Okay. So if we calculate that, one thing we might do is we might calculate its z-score, and then we could use the table that's similar to the one in the textbook that's listed right here. And this is the desired probability that we want to calculate. So here the peak is at 98.6. We want the probability it's bigger than 100 degrees. Okay. If you use your table, it typically lists less than probabilities, so you have to do the complement rule. Okay. So if we do this probability, we'll calculate the probability is bigger than 100. That's 1 minus the probability is less than 100. We'll calculate the z-score, and we'll get this number of 97.24, or about 2.76% of the temperatures are larger than 100 degrees. Okay, and if you use a table, it should look something like this. Okay, and you're going to look for the first two values of the z, that will be positive. Then you'll go across to calculate the next value of z, and you'll look for the value in this table for that corresponds to the z-score here. Okay, so you should have something similar to this in your textbook if you want to use the table. Okay, our next example are the heights of men that are aged 25 to 35, and we're told that they're normally distributed. They have a mean of 68 inches and a standard deviation of 5 inches. We calculate the probability that a randomly chosen man aged between 25 and 35 has a height between 65 inches and 73 inches. Okay, so we want to calculate that is between 65 and 73. You know, we could use a really good calculator, we could use the table, but the probability we want to calculate graphically is this one, and it corresponds to this area under the curve of the normal distribution with the parameters of the mean mu and standard deviation sigma given in this problem. So one thing that we might remark is that if we use the table, it only lists less than probabilities, but that probability we just showed is equal to these two probabilities. So we can subtract the probability x is less than 73 from the probability x is less than 65. And you only really need to do this if you use the table. Okay, so if we want to calculate this probability, we're going to get that it's less than 73 minus less than 65. We calculate the z-scores of each. We wind up with calculating the probability that a standard normal is less than 1 via the z-score minus the probability the z-score is less than minus 0.6. We can look up these two values in the table and get via subtraction that this is about 56% of men in this demographic. Okay, so that's a review of the normal distribution. Let's talk about the sampling statistic. So a sampling distribution is the probability, the distribution for all possible values of this statistic are computed from a sample. And that's a key word, a sample. And that's what makes it a sampling statistic. The probability we calculate represents how likely it is to observe certain values of the statistic. The statistic that we're most interested in here is the sample average. That is, we take all our values x1 through xn, we add them up, and we divide by n. Okay? So because each of the observations x1, x2, all the way through xn, because they're random, okay, before we collect any data, that makes our sample average also random. Okay. So whenever we have a random sample of observations, each with the same mean, so mu sub x, so that just means they have the same distributional mean and the same distributional standard deviation, the sample average from this population that is independent IID, so independent identically distributed, then it has a normal distribution, that is the sample average. And it's the mean of that normal distribution for the sample average is the same mean as each of the observations, but the standard deviation gets reduced by the square root of n. So its new standard deviation is right here. And that's a very important thing, is how that standard deviation changes. So generally, you want at least 30 observations, and this theorem, central limit theorem, applies no matter if our data is normally distributed or skewed if we have at least 30 observations. If it's not 30 observations, then the requirement is that each observation is normally distributed. Okay. Okay, so let's do an example problem here. So here the heights of men are again normally distributed with a mean of 68 inches and a standard deviation of 5. We're going to calculate the probability that in a random sample of 25 randomly chosen men in this population, that the average height is between 67 inches and 70 inches. So that is the average. So notice the sample size is less than 25, but we don't have to worry because the distribution of men's heights, we're told, is normally distributed. So the central limit theorem would apply if we had 5 observations and we took the sample average. It would apply if we had 10. So long as the underlying distribution is normal, the central limit theorem applies. Okay. So one of the most critical things when you apply the central limit theorem is to calculate the standard deviation of the sample correctly. So here, the standard deviation, the original one was 5, but then we have to divide by the square root of the sample size, which gives us this number of 1. So we want to calculate the probability the sample average between 67 inches and 70 inches. We do the subtraction again, and then we do the z-score. Now the z-score changes because our standard deviation changes to 1. So doing this tells us that there's an 81, nearly 82% probability the sample average in this situation will be between 67 inches and 70 inches. Okay. Okay. Now let's do one more example here, this time with body temperature. So the normal body temperature is 98.6 degrees Fahrenheit. We're going to assume the population standard deviation is 73 degrees Fahrenheit. And we're going to calculate the probability a randomly chosen sample of 30 individuals has a temperature that exceeds 100 degrees. So this is the sample average temperature for 30 individuals. What's the average temperature? And what's the probability that in a sample it exceeds 100 degrees? So the first thing to do when you're doing this type of problem is to calculate the standard deviation. So here it's 0.13. It shouldn't surprise us, the probability that the sample average is more than 100 degrees is 0, because the sample average, that should represent the population average, which is 98.6. The likelihood that for instance, one way that you could get it to exceed 100 degrees is that everyone has a temperature of more than 100 degrees. That's not the only way, but that is one way the sample average would be bigger than 100 degrees. And that's a pretty unlikely event, okay, for that to happen for so many individuals, okay. Now, it's certainly possible some of them have a temperature below the 98.6 and that a lot have a temperature more than 100 degrees and it averages out to be more than 100, but that likelihood is also very unlikely. It's 0, in fact. And if you were wondering how we could calculate this, you can use Python and use the stats package using the normal distribution calculator. And here I did the 1 minus because that's required in Python. It returns the less than or equal to probability. And and I calculated this probability here, but now I did it for a different probability because I didn't want us to give us all probabilities that were 0. Let's just calculate that it exceeds 98.8. 98.8 being close to the population average of 98.6. And so the first argument is the observed probability, 98.8. Then we fed in the mean of 98.6 and the standard deviation of 0.13. That gives us the 6.19%. Okay, so we could use Python to calculate probabilities, and here's an example of using the central limit theorem in Python to calculate a probability other than 0. Okay. So what if we don't know the population standard deviation? Well, the classical thing to do is to use the sample standard deviation. If you do that, right, this is very similar to the central limit theorem, except I'm using the sample S, sample standard deviation, instead of the symbol sigma. Okay, if I do that, I get what's called a t-distribution, and t-distribution always has degrees of freedom. The degrees of freedom are one less than my sample size. It shouldn't shock us that the t-distribution is related to the normal distribution, because as my sample size increases, I get a better and better estimate of a population standard deviation. So this converges to a normal distribution. The key difference is that the t-distribution has what's called a fatter tail. It has a higher probability for large values, as illustrated by this green curve. So for values bigger than 4, the t-distribution in this green line has a probability that, is much bigger than the blue curve, which has nearly no area um, for values bigger than 4. Okay, so these are all the terms that were used in the sampling distribution for the t-distribution. So notice it is a sampling distribution again, and we're going to calculate some probabilities with the t-distribution. So suppose now we return to the normal body temperature of 98.6. But now, instead of being told that it's the population standard deviation that's 0.73 degrees Fahrenheit, we're told it's the sample standard deviation. Well, then we have to use a t-distribution. So here again, we have x being the average body temperature, and we want to calculate the probability the average body temperature of 38 individuals exceeds 98.8 degrees Fahrenheit. So we're going to calculate the standard deviation. Again, it's 0.13. And we're going to calculate this probability with the t-distribution, that the sample average exceeds 98.8 is equal to the probability the t-distribution with 29 degrees of freedom exceeds this number listed here. And you have to calculate exactly what that value is. And you see that the probability is very similar to when we use the central limit theorem, but it's a little bit larger. It's 7.2%, which isn't that surprising that it's both close to the normal distribution when you use the central limit theorem, and that it's bigger because these t-distributions always have larger probabilities than the normal distribution for larger values. Now, we calculated this probability in Python from the stats package, and we calculated the probability the t-distribution exceeded this value. This is exactly what's here, okay? And we used the complement rule for the t-distribution because I used the cumulative distribution function. The cumulative distribution function is always less than or equal to, so I did 1 minus to it to get the larger than probability, and this 29 is the degrees of freedom. That gives me the 7.2%. There are many other calculators that you could use, or even tables. Okay, thank you very much.